Hello, chemistry students. So we are beginning our last big unit of the year, and it is on stoichiometry. All right, this is the unit that we were going to be doing in March, and I would much rather be doing it in person. It can be difficult for students, so this is definitely going to be a challenge. All right. The point of this video is just to introduce stoichiometry, what it is, what some of the questions will look like, and next week we will really work on the finer points of these questions. So stoichiometry, our definition of stoichiometry, all right, it's this Greek word. Stoichio means measuring. Metry is the study of, so it's in a way it's the study of measuring. Stoichiometry means representing the exact mass or moles of the reactants which are required to react with each other without any wastage, and also finding out the exact mass or moles of the product which will be formed. All right, so it's all about measuring. It's about mass, it's about moles, and it's about a chemical reaction. All right, so another definition, basically, the definition of stoichiometry is the mathematical way of finding the amount of chemical elements or compounds involved in chemical reactions. All right, and a side piece from this, stoichiometry is also sometimes described as the section of chemistry that deals with relationships of combining elements. If you remember when we did the empirical formula questions, right? We would do that little jingle, percent to mass, mass to mole, divide by small, multiply to whole. All right, that can be considered stoichiometry because it's looking at the relationship between elements being combined. All right, but we're really going to be looking at the chemical reactions in this unit. All right, so two things that you want to keep in mind as we move forward. You need to be comfortable with a chemical reaction, and we'll look at a couple examples. And we will be looking at mass to mole calculations. So mass divided by molar mass to give us moles, and moles times molar mass to go back to mass. But we won't do any of that in this video, right? We're just introducing stoichiometry. All right, so this is kind of an interesting image, and it does describe what stoichiometry is. If these two piles were to represent our reactants, right? The pile of red and the pile of green. When they combine, they're going to make the bluish purple and the more magenta. All right. So I want you to think, when you do a chemical reaction, you make something new. And we're going to have a little bit of leftover of the red, right? Which means we had more red than we needed up here. So this would be that waste. And the idea of stoichiometry would be, if we know the amounts of red and green and we know the reaction, we should be able to calculate all of these three products. We should be able to calculate how much of the purple, how much of the magenta, and how much red would be left over, right? That's the point of stoichiometry. It's adding this math piece to a balanced chemical reaction. All right, so it's important we're familiar with our chemical reactions, right? We have the reactants forming the products, where there's different types. We've seen that. This is a synthesis reaction because it's one product. We've seen decomposition, combustion, single replacement, double replacement. All right, I'm not going to be asking you the type of reaction. It's just something that we should know. Reactants forming products. And to balance the reactions, we add these coefficients, right? The coefficients come before the chemical formula. We never change any of the subscripts of any of the chemical formulas when balancing a reaction. We only change the coefficients. So here, this is a coefficient of 1. If there's no coefficient present, it's assumed to be 1. 3 H2s forming 2 NH3s. All right, so we need balanced reactions. That's very important. Just a reminder, when we think about a balanced reaction, it's the same number of atoms on each side of the reaction. So for hydrogen in this reaction up here, there's 4 hydrogen atoms as a reactant, 4 as a product, 2 oxygen atoms as a reactant, 2 as a product. All right, but we could start thinking of chemical reactions kind of like a recipe. All right, what this recipe is telling us is, if you have 2 H2 molecules and 1 O2 molecules, you can make 2 waters, 2 H2Os. Now, what if I had 4 H2s? All right, how many O2s would I need to react with 4 H2s? Well, the ratio, it's 2 to 1. So if I had 4 H2s, I would need 2 O2s. All right, 2 to 1 ratio. And how many waters would I make if I had 4 H2s? Well, it's a 2 to 2 ratio. So however many H2s I have, that's how many H2Os I'm going to make. So if I had 4 H2s, I'm going to make 4 H2Os. That would be a really simple stoichiometry problem. So it leads us, and this is the most important piece to get out of this video. It leads us to the mole ratio. The mole ratio is the ratio of reactants and products and is the ratio of the coefficients for reactants and products found in the balanced chemical reaction. All right, the mole ratio is based on those coefficients, which is why we need the proper coefficients, all right, to do a reaction, which is why we need the balanced chemical reactions. All right, so in the reaction given, we have 2 magnesium plus 1 oxygen yields 2 magnesium oxide. The ratio is of magnesium to magnesium oxide. It's 2 to 1 to 2. All right. Now, mole ratios, we have a new reaction here, and we're going to stick with this reaction for a little while. We have aluminum oxide decomposing to yield aluminum plus oxygen. Balanced, the coefficients are 2, 4, and 3. So the ratio of aluminum oxide to aluminum, it's 2 to 4, and we can write it as a fraction, and we can flip it. It could be 2 mole 2A Al2O3 over 4Al, or it could be 4Al over 2 Al2O3, right? These fractions, based on how we need them to appear, we can switch them around. The ratio of aluminum oxide to oxygen, it's 2 to 3, so we could do 2 over 3 or 3 over 2. And the ratio of aluminum to oxygen, it's 4 to 3. So the ratios can be 4 over 3 or 3 over 4. And I'll show you why we're allowed to change these fractions, but the fractions are what we are going to want. All right, so let's stick with this reaction, all right? The aluminum oxide, it's also called alumina molten. All right, when we run an electric current through it, it will form aluminum metal and it will form oxygen gas. All right, so let's just think about a couple of simple questions. If I have 10 molecules of Al2O3, right, 10 molecules of aluminum oxide, how many atoms of aluminum will I get as products? All right, let's think about the ratio. For every 2 aluminum oxides, I get 4 aluminum atoms, right? So for every 2 aluminum oxides, I get 4 aluminums. So that's a 2 to 4 ratio. So it's twice as much, right? I get twice as much aluminum metal for every 1 aluminum oxide. So I have 10 molecules, and here's how I'm going to set up my mole fraction, or my ratio. I'm going to put the aluminum on top because that's what I want, right? So we're going to be using that same want over given setup, right? We've used this in unit conversions before. So the thing I want is going to go up top. Al2O3, aluminum oxide, I'm going to call that my given, right? It's the given information in the problem. So it's going to go on the bottom of my fraction. So want up top over given, and it's the coefficients from the balanced reaction. So 10 molecules of Al2O3 times 4 over 2, right, which is really just times 2, it gives me 20 aluminum atoms, right? So for every 2 aluminum oxides, I get 4 aluminum atoms, all right, 2 to 4 ratio. If I have 10 molecules, I'm getting 20 atoms. All right. Now, what if I have 1,500 molecules of aluminum oxide, right? 1,500 aluminum oxide molecules. How many atoms of aluminum will I get as products? I can set up the exact same type of math, right? Now, my given information is 1,500 molecules of aluminum oxide. But I still want aluminum in this product. I'm still given aluminum oxide. I put the coefficients in their respective spots, right? So 4/2, that's that 4:2 ratio. And then I can just multiply. Now this is where a calculator is going to be handy. So you're going to want a calculator for this entire unit. 1,500 times 4 is going to give me 6,000. 6,000 divided by 2 is going to give me 3,000. And look at this. The given substance, aluminum oxide, gets canceled out, which is why I want to label my answer 3,000 Al, right? Just like how it appeared in the balanced reaction. All right, so we can use individual molecules. That's totally fair. All right, now look at this question. If I have 4 dozen Al2O3 molecules, how many aluminum atoms will I get as products? All right, you might distribute. You might be, okay, Mr. L, 4 dozen, that's 4 times 12. I can do that in my head. That's 48. But I don't want to write 48. All right, I'm going to leave it as 4 dozen. All right, 4 dozen aluminum oxide, and I'm putting the exact same mole ratio. All right, the substance that I was given in the problem, aluminum oxide, is going on the bottom. The substance I want to find, pure aluminum, is going on top, and their coefficients from the balanced reaction are making up that ratio, right? So what's 4 dozen times 4? That's 16 dozen. What's 16 dozen divided by 2? 8 dozen, right? 8 dozen aluminums. So we can use something like the dozen because it's a counting unit, right? A dozen always means 12, all right? What's the other important counting unit that we have learned this year? The mole, all right? So this is like the true part of stoichiometry, moles. If I have 6.8 moles of aluminum oxide, how many moles of aluminum metal can I make? All right, so I start with 6.8 moles of aluminum oxide. I write it in just in the same spot. I don't have to do anything fancy here. My ratio is the same, all right? For every 2 aluminum oxide, I get 4 aluminum. It's 4/2. It's still the same given and the same substance that I want. I'm going to multiply them, 6.8 times 4. I'm then going to divide by 2. I'm going to get 13.6 moles of aluminum, right? And 13.6 moles of aluminum is going to be something that we could measure in a chemistry lab, because we can't measure 10 molecules. We can't measure 1,500 molecules. We can't measure 4 dozen molecules, but we can measure 13.6 moles, right? So this is the point, and the given substance gets canceled. The substance we want to find stays behind. All right, so here's the formula. Moles given times coefficient of the substance you want divided by the coefficient of the substance given will equal moles of want. All right, and again, givens will cancel out and we will be left with our want. So I just want to leave you with one last metaphor as we introduce the topic of stoichiometry. Think about making a grilled cheese sandwich. 2 slices of bread plus 1 slice of cheese equals a grilled cheese sandwich, okay? Maybe you like 2 slices of cheese. Maybe you like 5 slices of cheese. I don't know. This is the grilled cheese we're making. We're keeping it simple. 2 slices of bread, 1 slice of cheese. There's your grilled cheese. All right? Look at this question, right? We have it written as a equation. 2 bread plus 1 cheese equals 1 sandwich. No numbers in front of the cheese or the sandwich, so that's how we know. We can assume it's a 1. How many slices of bread do you need to make 7 grilled cheese sandwiches? All right, 7 grilled cheese sandwiches is the given info. So 7 sandwiches times a mole ratio of 2 bread, the thing we want, over 1 sandwich given, right? And the 2 and 1 come from the balanced reaction. 7 times 2/1 equals 14 slices of bread. All right, this is a very simple example, but if you wanted 7 grilled cheese sandwiches, you're going to need 14 slices of bread. And that's stuff that you know, because you know grilled cheese well, but you might not realize it when you look at a chemical equation, which maybe aluminum oxide forming aluminum and oxygen is a little more foreign to you. All right. One last slide I want to leave you with. All right. We can also do this with cookies. All right. To make 12 cookies, 12 chocolate chip cookies, you need 1 cup of flour plus 4 eggs plus a half cup of sugar plus 1 cup of butter plus a half cup of chocolate chips. I don't know if that's exactly how it'll work. All right, but that looks good. And it'll make you 12 cookies. Well, what if I only wanted 1 cookie? In theory, we can scale the recipe, right? So we can multiply everything by the same number. So here, since I only want 1/12 of the total numbers of cookies, I'm going to take my 1 cup of flour, I'm going to divide it by 12. I'm going to take my 4 eggs, I'm going to divide it by 12. 4 divided by 12 is going to be 1/3. I'm going to take my half cup of sugar, I'm going to divide that by 12. 1/24 a cup of sugar. I'm going to take my 1 cup of butter, I'm going to divide that by 12, right? 1/12. My half cup of chocolate chips, I'm dividing that by 12, 1/24. And my 12 cookies that I should make, I'm now dividing by 12 as well. That's going to be just 1 cookie. So next week in our lab, we will look at a recipe and we'll try to scale it in the opposite direction. Instead of reducing it, we'll take a recipe that makes 20 cookies and we'll figure out how much we would need, let's say, to make 150 cookies. All right, so stay safe, guys. This is an intro to stoichiometry. We will see more of it next week. Do the practice questions just looking at mole ratios.